So this time we're going to prove this formula of McMahon's. Again, we have the major index, which is going to be this permutation statistic that adds up the positions of the descents. That's kind of a bizarre notion, but it has this beautiful formula giving us the classic Q analog of n factorial. So this is our aim to prove this today. And the first step in our proof, following McMahon's proof, is going to be to rewrite the right-hand side. Because I'm going to remind you that the Q integer n, while of course it is this expression, it also can be written as 1 minus Q to the n divided by 1 minus Q. Okay, because when we do long division, that's exactly what we get. So we can rewrite n factorial in another way. So if we change this to n factorial, the numerator's got 1 minus Q to the n, 1 minus Q n minus 1, all the way down to 1 minus Q, and on the denominator, what do we get? Well, we get 1 minus Q n times. Okay, so that's another way to write the right-hand side of this expression of McMahon's. Now, why would we want to do this? It looks less combinatorial unless you keep in mind that these are generating functions. And so we can think about this very combinatorially. This is just the generating function for the number of sequences of length n, right? Where 1 over 1 minus Q is just pick a number from 0 to infinity, pick a number from 0 to infinity, do it n times. That's weak compositions of n. This numerator is not so combinatorial, but if it were a denominator, then we've seen it before. This is the partition generating function where the biggest part of your partition is size n. So let's rewrite McMahon's formula, moving things around a little bit to the way that he actually expressed this. So that's going to be the sum of W and Sn, Q to the major index of W, divided by, I'm moving that numerator over to here, so this is going to be 1 minus Q squared, all the way up to 1 minus Q to the n, is equal to 1 over 1 minus Q to the n. So this is a nice clean formula. This is actually what we want to prove. This is equivalent to McMahon's theorem. And now again, we're going to interpret these guys combinatorially, so let's maybe make notes of that. Over here, this is just the composition generating function, right? So this is compositions into n parts. So this is sequences in n to the n, okay? Where bold n means the non-negative integers. Okay, and then the denominator here, this part, is partitions lambda such that lambda 1 greater than or equal to lambda 2 greater than or equal to greater than or equal to lambda k greater than 0. So these are partitions where the first part is at most n. And again, the reason is this is the partition generating function. This is how many 1s do you take, how many 2s, all the way up to how many n's do you take. Okay, and now we know the numerator here is permutations. So if we want to take the coefficient of Q to the n on both sides, what do we get? Well, on the left-hand side, we're going to take a permutation and a partition. And the n means we need to have that the major index of the permutation plus the size of the partition. That's what contributes to the degree, has to equal n. And again, we have the caveat that here we want lambda 1 to be less than or equal to n. So these are the objects that we're getting on the left-hand side over here. And on the right-hand side, these are just going to be the compositions alpha 1 up to alpha n, where the sum of the alpha i's is n. Okay? And of course, these alpha i's are non-negative integers. So really what we want to do is we want to construct a bijection. So we want a bijection that goes from compositions of capital N, some number capital N, that's going to tell me what my coefficient, into n parts. I'm actually doing my bijection backward from the way I've written it above, to pairs of a permutation and a partition such that the partition has to have biggest part n, and when I add up the major index of the permutation with the size of the partition, I get capital N. Okay, so let's do an example of how this bijection goes. I'd rather do an example and then we can dive in to the definition, but I think it's more clear when we look at an example. So let's start with our composition alpha. So I could take alpha, for example, to be 5, 1, 0, 2, 3, 0. In this particular case, we're going to have n, the length of the composition is 6, and capital N, the size, is 11. 5 plus 1 plus 2 plus 3, plus a couple zeros. Okay, the easiest thing to define is my permutation. So W is going to be sort alpha to weakly decreasing in the minimal way. So perhaps it's not obvious to you that there's a unique minimal way to do it, and it doesn't matter how I do it as long as I don't do anything stupid, but it's in fact true. So I'm going to sort alpha to weakly decreasing. In this particular example, this is going to turn alpha into something that I'm going to call A, 5, 3, 2, 1, 0, 0. So what's the minimum bubble sort, if you want to think of it that way, and what's the permutation that achieves that? The permutation that achieves that for this particular example is the permutation, well, let's maybe actually do it. So we can do 5, 1, 0, 2, 3, 0. If we think about how we sort this guy, we can sort any out of order pair. So anytime we have a pair that's out of order, we can sort it, and it doesn't matter which order we do this in. So I'll just keep going here till I get it done. 5, 2, 1, 3, 0, 0. 5, 2, 3, 1, 0, 0. 5, 3, 2, 1, 0, 0. So the number of steps it takes me is going to be the number of inversions of my permutation, if I've done it correctly. And so my permutation in this case, I can just think about at each step which two numbers did I transpose, and I can do that to the permutation. And so what I get for this example is W is equal to going to be a fixed point, 5, 4, 2, 3, 6. Okay, and then you can just, if you want to double check, inversions, 5 contributes 3 inversions, the 4 has 2 inversions, and they correspond to the 5 steps that we took. Okay, so that's W. Easy enough to get. And now what is the partition lambda? Well, to get lambda, I'm going to build up, I've got this guy A, and now I'm going to build up something that I'm going to call C, and that's going to tell me the multiplicities for the parts. So C is going to be C1, C2, all the way up to Cn. Okay, and Ci is going to be the number of parts of lambda that are size I. And I'm going to define it based on this A, which is the sorted version of alpha that I began with. And the rule is going to be that Ci is either going to be AI minus AI plus 1, or AI minus AI plus 1 minus 1. It's either the difference or one less than the difference. It's the difference whenever I don't have a descent in my permutation, and it's going to be the other case whenever I do. Okay, so let's see how that builds up. So if I look at C1, so here's my permutation W, right? So let's mark our descents. So let's get our descents in here for W. So here's a descent, here's a descent, and those are my only descents for this particular example. So MAJ of W, maybe I'll go ahead and make a note of this, is equal to 2 plus 3 equals 5. Okay, so keep in mind that my MAJ and the sides of my partition are supposed to add up to this capital N, 11, so I've got 6 left to do. So I'm going to end up with a partition of 6 when I do this properly. So let's go back over here and say, okay, well, what is C1? Let's build up C1. Well, I don't have a descent from position 1 to position 2. So I don't have a descent here, so I'm in this first case. So I'm going to take the difference of the A's, which here is 2. So this is going to be 5 minus 3. And that's because 1 is less than 5. 5 is bigger than 4, so I'm in the second case. So I'm going to have 3 minus 2 minus 1. And I can see that I'm going to run out of space here. So let me go ahead and scoot this guy over for us. And then I'm in the second case again, which is going to give me 2 minus 1 minus 1. And then I'm in the first case, which gives me 2 minus 1. And then I'm in the first case again, which is going to give me Oh, sorry. It's 1 minus 0. 1 minus 0, and this is going to give me 0 minus 0, and 0 again. So now when I look at this, I say, okay, well, what have I got here? I've got 2, 0, 0, 1, 0, 0. So what is my partition lambda? My partition lambda is going to have 2 1s and a 4. So it's going to equal the partition 4, 1, 1, which indeed has size 6. So the image is going to be the pair 1, 5, 4, 2, 3, 6, comma, 4, 1, 1. That's the image of my map. The major index, which we already computed here, the major index of this guy is 5. The size of lambda is equal to 6. And 5 plus 6 is equal to capital N. So you can check that this is indeed a bijection. And you know, there's a little bit to go through here, and it's actually a good exercise to check why this construction of C that I have over here, why does this construction work? Right? That's a good thing to go through for yourself. Why is that always going to give me the complement of the major index? And it's exactly because here what I'm doing is I'm saying, okay, well, I'm saying when I have a descent, I'm going to decrement my difference, and when I don't have a descent, I'm going to leave it alone. So look at how this goes through this example, and then you can convince yourself that this is true. Maybe write up your proof, but we'll consider that our proof. So we have now proven McMahon's formula. And again, another way to say it, and maybe I'll write it again because things have gotten cluttered on that side, is that W and Sn of Q to the maj of W is equal to the Q integer factorial. And we'll do another bijection that puts the major index in bijection with inversion number in the next video.